So I was doing these and I thought if I'm doing them anyway, I might as well do this for these as well. I did good on my AccuPlacer. I only had to take the math, it turns out, and I did fine. I did great. They had 5 levels I could have gotten, and I got the second, not the first. That's great. I'm happy with the results. So 271 is what I got. But I didn't have to do the English because I got it from English course I took a while back and a million years ago. So that was good. So that stuff is done. So now I'm moving on to, I want to use CLEP to get some courses done. So I've never done this before, but we'll see how it goes. And I'm using Modern States because it seems to, well, if you get 75% or more on their test, then they will pay for the CLEP, which is great. And it's a good review, so we'll see. A lot of people seem to use it, I guess. So I'm going to turn my microphone off and just watch these shows at 1.5 speed. I'm doing math right now. I'm going back and forth between math and English, and it's not, I don't think I'm going to do algebra. I think I'm going to do what they call college math, which is a nice overview of the fun stuff of mathematics, which is more of my speed, I think. Okay, I don't want to get an echo, so let me turn this off.
Another class of functions and the equations corresponding to them. And this is the exponential and log cubed, x squared, x to the 100. So they actually look quite different and have very different behaviors. We will also discuss logarithms, which are somehow inverse to exponentials. So what does it mean to say that y is equal to the logarithm base a of x? This is just a compact way of saying that if I take a number a and raise it to the yth power, I get x. So in a very concrete sense, logarithms and exponentials are inverses. So commonly logarithms are used as a tool, right? They're used as tools to solve exponential equations. And then finally, we have 2 in the exponent right here. So this is the term that really makes it complicated, this ax squared, right? So keep in mind that a, b, and c are what are called coefficients. And they will typically be defined for a particular problem. And they're not what makes it complicated. It's the powers of x that make things somehow complicated for us. Right? So we will develop something called the quadratic formula for working with second order polynomials that I like to abbreviate as QF. Once we finish with quadratics, we'll look at another class of functions and the equations corresponding to them. And this is the exponential and logarithmic functions. Okay, so exponential functions look like y equals a to the x, where a is a fixed base. So you can think of a as constant here, and x is the variable. So exponential functions, on the face of it, look a little bit like polynomials, but they are actually quite different. So an exponential function could be something like 2 to the x, 3 to the x, something called e to the x is another famous example, versus polynomials don't have the variable in the exponent. These are things like x cubed, x squared, x to the 100. So they actually look quite different and have very different behaviors. We will also discuss logarithms, which are somehow inverse to exponentials. So what does it mean to say that y is equal to the logarithm base a of x? This is just a compact way of saying that if I take a number a and raise it to the yth power, I get x. So in a very concrete sense, logarithms and exponentials are inverses. So commonly logarithms are used as a tool, right? They're used as tools to solve exponential equations. And then finally, we will study the absolute value. Okay, this sometimes seems complicated and challenging, but actually I think has a very simple formula. It just says whatever your input is, if it's positive, leave it alone. If it's negative, drop that negative sign. So the absolute value of a would be equal to a for a greater than or equal to 0 and minus a for a less than 0. So as an example, the absolute value of minus 2 is 2, and the absolute value of 2 is 2. So absolute value says if there's a minus sign, kill it off. If there's no minus sign, don't do anything to it. So we will discuss both equations and inequalities. Now, in many ways, they're solved the same way. In fact, what we'll do is for inequalities is essentially solve an equation first, and then make some slight modifications at the end to address the fact that we actually have an inequality versus an equation. Okay? So just to be totally clear, what do we mean by equation? We mean something like f of x equals, say, a constant a. What do we mean by an inequality? We mean something like a function f of x is less than or equal to some constant a, or greater than or equal to. So how do these solution sets differ? That is, if I give you something like f of x equals a, what would you expect to get as a solution? Well, you would expect something like a discrete set of points. So finitely many points are typically solutions to equations. So for example, let's be real simple and say that f of x is equal to x plus 1. And I want to solve the equation f of x equals 0. Well, okay, I can do this with some nice algebraic manipulations. I can say x plus 1 is equal to 0, which means that x is equal to minus 1. And the point I want to illustrate here is that this equation has a single point as a solution. In distinction, inequalities typically have regions as solutions. So instead of having one particular or a finite set of particular solutions, I get infinitely many solutions corresponding to all the points in some region. So let's look at a related example. Let's say I had f of x was again equal to x plus 1, and I wanted to solve the equation f of x less than or equal to 0. Well, I solve it in much the same way. I would say this means x plus 1 should be less than 0, so x ought to be less than or equal to minus 1. So now I don't get a single point, I get infinitely many points. Minus 1 will work, so will minus 2, so will minus 3, and so on. So this is very different structurally. Equations typically have a discrete set of points as solutions. Inequalities typically have infinitely many points as solutions, and they correspond to a region of the real line, for example. Now, in this case, it was quite easy to just sort of add and subtract minus 1 to both sides to solve them, these equations and inequalities. Sometimes you'll be encountering equations that are not so obvious, where a specific formula can be very helpful for us. So we'll focus next on what's called the quadratic formula, which is specifically designed to handle second-order polynomials, which are pretty tricky without it. We'll look now at a very famous mathematical formula. It's called the quadratic formula. So called because it gives us a way of solving quadratic polynomials, or second-order polynomials. Right, so again, the quadratic here is referring to second-order polynomials. So what does this formula allow us to do? Well, it allows us to solve equations that look like the following. 0 equals ax squared plus bx plus c. So this is a generic second-order polynomial. And what our formula says is kind of remarkable. It says that all I need to do to be able to solve this is plug my coefficients into this formula. So take a, b, and c and run them in the following formula. The solutions are going to be x equals minus b plus or minus, this is important, square root of b squared minus 4ac, and then I divide everything by 2a. So the plus minus here says one solution will look like negative b minus square root of b squared minus 4ac over 2a, and another solution, so I'll call this x1, I get another solution, x2, given by negative b plus square root of b squared minus 4ac over 2a. So that plus minus tells me that in almost all situations, I don't just get one solution, I get two. One corresponding to the negative branch, one corresponding to the positive branch. Now there is sort of an exceptional case in which you only get one solution. And it's when this plus minus doesn't matter, because what comes after it is 0. That is, when square root of b squared minus 4ac is equal to 0, I only get one solution. So we give a special name for this quantity that determines that. So this b squared minus 4ac is called the discriminant, which is a useful term to know for the CLEP. Sometimes they ask about this. So it discriminates between two cases. Case 1, I'll call it, and case 2. So case 1 will be one solution. Case 2 will be two solutions. As long as b squared minus 4ac is not 0, you'll get two solutions. If it's 0, you only get one. So let's look at a few examples of second-order polynomials and using the quadratic formula. So here I have x squared minus 7x plus 9. All I need to do to solve this is to run these coefficients in the formula. So it's helpful, at least when you're beginning, eventually you get good enough to not have to do this, to write out what the coefficients are so that the substitution into the formula is more straightforward. So let's see what a, b, and c are. So a is the coefficient on x squared, which is 1 in this case. If you don't see a coefficient, it's because the coefficient is 1, and multiplying by 1 does nothing. B is minus 7, that's the coefficient here, and c is equal to 9. And now all we have to do is plug into the formula. So I know that x equals negative b, so negative negative 7, plus or minus square root of minus 7 squared, minus 4 times a is 1, c is 9. Right, and now all I'll do is I'll simplify this out, and we'll get hopefully a nice solution, maybe not so nice. So this is negative negative 7 is positive 7, because the negatives cancel, plus or minus square root of 49, minus 4 times 9 is 36, divided by 2. And then 49 minus 36 is 13, of course, divided by 2. And there's actually nothing else we can really do with this, because square root of 13 does not simplify any further. It does not contain a perfect square. So I'll say square root of 13 cannot be simplified. And I'll say this is because it has no perfect square factors. If you don't know what that means, it's not really very important for the CLEP, but it is sort of interesting in its own right. Okay? So let's move on to a second example. Now in this case, we have actually a leading coefficient other than 1. Right? So the coefficient on x squared for these is sometimes called the leading coefficient. Leading because it's the coefficient on the highest order term. In the previous example, it was 1. Here it's 2. But we'll play the same game. We'll write out what each of the coefficients are, and then we'll plug into the formula. So in this case, a is equal to 2, b is equal to 1, and c is equal to negative 3. Okay, so then x is equal to negative b, so negative 1, plus or minus b squared is 1 squared, minus 4 times a, which is 2, times c, which is minus 3, divided by 2 times a, which is 2 now. So a lot of times these polynomials are what you would call monic, which means that the leading coefficient is 1. In this case, it's not. So you do have to do something in the denominator. It's not 2 times 1, it's 2 times 2. But now we're going to do the same thing as before. We are going to simplify each of the individual pieces in the formula and see what pops out. So let's take a look inside of the square root sign. So 1 squared is 1. 4 times 2 times minus 3 is, let's see here, positive 24. And then 2 times 2 is 4. So do a little more simplification under the square root sign. 1 plus 24 is 25, divided by 4. Let's continue over here. And then it's good to remember sort of your what are called perfect squares. So things that have square roots, when I take the square root, I get an integer back, a whole number. So in this case, we know that square root of 25 is 5, and then I divide by 4. Okay? So and you could leave it like this. You can also split it up and say, well, I get minus 1 plus 5 over 4, and minus 1 minus 5 over 4. So I get 1 and then negative 3 halves. Or you can leave it like this. So again, we get two solutions in this case. And in fact, one of them is positive, one of them is negative. That's not always the case. Sometimes it does happen that they're both positive or both negative, but it is possible that you get one of each. So we'll look now at another family of equations, those related to exponents and logarithms. So what we'll do is we'll start by reviewing some of the basic properties of both of these and then look at a handful of equation examples. So let's start with exponentials, right? So just to recall, these are things like 2 to the x, so examples, 2 to the x, 3 to the x, even something like 2 to the negative x. And then I'll bring up now an important example called e to the x. So e is a special number that's approximately 2.71. It's called Euler's constant. And it's sort of one of those special numbers in mathematics that seems to appear in many different contexts. It appears naturally in calculus in particular. It comes up just sort of in many different situations, sort of unexpectedly. It is a very complicated number, sort of like pi. In our very last module, we'll discuss rational and irrational numbers. E is an example of an irrational number. It's actually even more complicated. It's what's called a transcendental number. So I'll say it is infinite, and it is transcendental. which is definitely not a topic covered on this exam, but it's sort of interesting to know, I think. And I'll say it's transcendental like pi. But it's often used as the base of exponentials. It just seems to come up in many different ways. Okay, so you should certainly be familiar with, if you see e to the x, what they mean is an exponential formula where the base is like 2.71 approximately, though this decimal does go on forever and never repeats. Okay, so let's look at a few basic properties of exponentials. Of course, some of the most important are how addition in the exponent works. So it says if I have two things I'm adding in the exponent, this splits as a product on the outside. So for example, 2 to the 3 plus 1 is equal to 2 to the 3 times 2 to the 1. So 8 times 2, so 16. Okay, I mean, of course, you may have just known that 2 to the 4 was equal to 16. Okay, but this basically gives us a general way to say if I have addition in the exponent, it comes outside as multiplication. Now I have to ask, okay, what happens if I have multiplication outside? What if I have a to the x times b to the x? Well, as long as this x is the same for both of these, I can multiply the bases. Okay, so for example, 2 to the x times 3 to the x is equal to 2 times 3 to the x, so 6 to the x. Something else we can look at is what's called iterating exponentiation, where I have a to the x, and then I raise it to the yth power. What does this do? I would call this iterated exponents because first I hit a with x in the exponent, and then I hit it with y. So what's this like? Well, it turns out it's the same as just exponentiating one time, but what you exponentiate is x times y. Right? So this is equal to a to the power x times y. So for example, if I have 2 squared to the third, this is the same as 2 to the 2 times 3, so 2 to the sixth. Okay, so that's the kind of example you maybe want to keep in your mind. And then one sort of basic foundational point, which is anything raised to the 0th power is 1 by convention. Okay, so that's this here. All right. So we can look now at the inverse of exponentials. We can look at logarithms, which have very related rules. And in fact, one can prove the rules for logarithms just using the rules for exponentials. Right, so let's just recall what a logarithm stands for. So if I have y equals log base a of x, this is shorthand and equivalent to a to the y equals x. Okay? So a is called the base of the logarithm. You can, in general, pick any positive number to be the base, but certain logarithms are more common than others. Certain choices of bases are very, very common. Some natural ones include 2. This is very common in computer science because you have binary notation for numbers, so 2 is very natural for this. So we'll say, so common bases, a equals 2, so we get the log base 2. Another common one is 10, so you get log base 10. Sometimes this one is written without a base. They just write log. Okay? That's because 10 is the base of our number system. Right? We go with ones, then tens, then hundreds, then thousands. So 10 is somehow universal to the way that we Westerners write numbers. Okay? So we call this sometimes the common logarithm. And then the other one that's kind of strange, if you're not familiar with it, is again this number e. So if I take a to be e, so approximately 2.71, then I can talk about the log base e. This gets a special name. It gets ln for natural logarithm. So these are the 3 you're most likely to see. Base 2 because of its applications to computer science, base 10 because of its connection to our number system, and then the natural logarithm base e just because of e's pervasiveness in mathematics. Okay, so let's look at the formula. They're very related to the exponential formulas. Here it says, okay, if I have a product of things that I'm taking the log of, it splits as a sum outside. So for example, log base 10 of 20 times 10 is equal to log base 10 of 20 plus log base 10 of 10. If I have a quotient here instead of a product, it works the same way, except I have a subtraction sign, and here I have an addition sign. If I have an exponential, right, so if I'm taking the logarithm of something like x to the power y, what's beautiful about logarithms is that power y comes down outside of the logarithm as a product. So this y comes down here, and I get y times log base a of x. And then we have a few sort of foundational points. Log base a of 1 is 0, and log base a of a, this is not 0, it should be equal to 1. Okay? So these are just a few kind of basic building blocks to play with logarithms and exponentials. So now that we've sort of gone through the mathematical theory briefly, let's look at a few examples and try and apply these tricks and rules to solving equations. So here's one. We have an exponential equation. 3 to the power x squared minus 1 should be equal to 1. Okay? I think this is very, very difficult to try and just guess your way to the solution. Okay? What we want to do is use our properties of logarithms and exponentials to solve this. So recall that logarithms and exponentials undo each other. So to solve this equation, what I'm going to do is hit both sides with an appropriately chosen logarithm. My exponential is 3, so I'll hit it with log base 3. So let's take a look here. So I'll say this is log base 3 of 3x squared minus 1 equals log base 3 of 1. Okay? So what is happening on the left-hand side? Well, the log base 3 is going to kill that exponential. So I'll just get x squared minus 1 on the left-hand side. How about on the right? I need to identify log base 3 of 1. Well, this is 0, right? Because log base a of 1 equals 0 for all a. Okay. And now I just have to solve this. So you can solve this with the quadratic formula if you wanted to. You can also do what's called factoring and write this as x plus 1 times x minus 1 equals 0 and determine that x equals minus 1 or 1 are my solutions. And we can check this. If I plug in x equals 1 into the original equation, I get 3 to the 1 squared minus 1, so 3 to the 0, which is 1, as desired. And then same with minus 1. If I plug it in, I'll get 1 on the left-hand side. So here the key trick was to use logarithms. Let's look at a similar equation. So here I have an exponential of 2.